Hello everyone, today we're diving into a hands-on experiment, building a low-pass filter using an operational amplifier, or op-amp. We'll use a signal generator to input sine waves at different frequencies, and an oscilloscope to measure the input and output signals. This will help us understand the filter's frequency response and compare ideal Bode plots with real experimental results. First, let's look at the circuit setup. We use an op-amp with a resistor and capacitor to create a first-order low-pass filter. The cutoff frequency is calculated as 1 over 2 pi times R times C. Now onto the experiment. We start with the low-frequency input. On the oscilloscope photo, the output waveform matches the input almost perfectly, no amplitude attenuation and minimal phase shift. This shows low frequencies pass through easily. Next, medium frequency near the cutoff. The photo shows the output amplitude starting to decrease, with a slight phase delay. Calculate the gain, output amplitude over input, then in decibels as 20 times log base 10 of that ratio. This is the transition region of the low-pass filter. Then high frequency above the cutoff. The oscilloscope image clearly shows significant amplitude attenuation and a phase shift approaching -90 degrees. But notice at high frequencies, there's often noise in the signal, which can cause some discrepancies between theory and practice. High frequencies are blocked, as expected from a low-pass filter. From these measurements, we extract amplitude ratios and time delays at each frequency to compute gain in decibels and phase in degrees. Plotting multiple points gives us the experimental Bode plot. Now, comparing to the ideal Bode plots, the magnitude should be flat at 0 decibels below cutoff, then roll off at -20 decibels per decade. Phase starts at 0 and approaches -90 degrees. Our experimental results match closely, but minor differences arise from real-world factors like component tolerances and that high-frequency noise we mentioned. This experiment is super practical for electrical engineering students or DIY enthusiasts. You can try it at home with a breadboard and basic lab tools. If you enjoyed this, like and share. See you in the next video.